Chapter 2 Aerodynamics, Aircraft Assembly, and Rigging. Introduction. 3 topics that are directly related to the manufacture, operation, and repair of aircraft are aerodynamics, aircraft assembly, and rigging. Each of these subject areas, though studied separately, eventually connect to provide a scientific and physical understanding of how an aircraft is prepared for flight. A logical place to start with these 3 topics is the study of basic aerodynamics. By studying aerodynamics, a person becomes familiar with the fundamentals of aircraft flight. Basic aerodynamics. Aerodynamics is the study of the dynamics of gases, the interaction between a moving object and the atmosphere being of primary interest for this handbook. The movement of an object is its reaction to the airflow around it can be seen when watching water passing the bow of a ship. The major difference between water and air is that air is compressible and water is incompressible. The action of the airflow over a body is a large part of the study of aerodynamics. Some common aircraft terms, such as rudder, hull, waterline, and keel beam, were borrowed from nautical terms. Many textbooks have been written about the aerodynamics of aircraft flight. It is not necessary for an airframe and power plant A&P mechanic to be as knowledgeable as an aeronautical engineer about aerodynamics. The mechanic must be able to understand the relationships between how an aircraft performs in flight and its reactions to the forces acting on its structural parts. Understanding why aircraft are designed with particular types of primary and secondary control systems and why the surfaces must be aerodynamically smooth becomes essential when maintaining today's complex aircraft. The theory of flight should be described in terms of the laws of flight because what happens to an aircraft when it flies is not based upon assumptions, but upon the series of facts. Aerodynamics is a study of laws which have been proven to be physical reasons why a plane flies. The term aerodynamics is derived from the combination of 2 Greek words, aero, meaning air, and dyne, meaning force of power. Thus, when aero joins dynamics, the result is aerodynamics, the study of objects in motion through the air and the forces that produce or change such motion. Aerodynamically, an aircraft can be defined as an object traveling through space that is affected by the changes in atmospheric conditions. To state it another way, aerodynamics covers the relationship between the aircraft, relative wind, and atmosphere. The atmosphere. Before examining the fundamental laws of flight, several basic facts must be considered, namely that an aircraft operates in the air. Therefore, those properties of air that affect the control and performance of an aircraft must be understood. The air in the Earth's atmosphere is composed mostly of nitrogen and oxygen. Air is considered a fluid because it fits the definition of a substance that has the ability to flow or assume the shape of the container in which it is enclosed. If the container is heated, pressure increases. If cooled, the pressure decreases. The weight of air is heaviest at sea level when it has been compressed by all of the air above. This compression of air is called atmospheric pressure. Pressure. Atmospheric pressure is usually defined as the force exerted against the Earth's surface by the weight of the air above that surface. Weight is force applied to an area that results in pressure. Force, F, equals area, A, times pressure, P, or F equals AP. Therefore, to find the amount of pressure, divide area into force. Pressure equals force divided by A. A column of air, 1 square inch, extending from sea level to the top of the atmosphere, weighs approximately 14.7 pounds. Therefore, atmospheric pressure is stated in pounds per square inch, psi. Thus, atmospheric pressure at sea level is 14.7 psi. Atmospheric pressure is measured with an instrument called a barometer, composed of mercury in a tube that records atmospheric pressure in inches Hg. Figure 2.1. The standard measurement in aviation altimeters in U.S. weather reports has been inches Hg. However, worldwide, weather maps and some non-U.S. manufactured aircraft instruments indicate pressure in millibars, MB, a metric unit. At sea level, when the average atmospheric pressure is 14.7 psi, the barometric pressure is 29.92 inches mercury, and the metric measurement is 1013.25 millibars. An important consideration is that atmospheric pressure varies with altitude. As an aircraft ascends, atmospheric pressure drops. Oxygen content of the air decreases and temperature drops. The changes in altitude affect an aircraft's performance in such areas as lift and engine horsepower. The effects of temperature, altitude, and density of air on aircraft performance are covered in the following paragraphs. Density. Density is weight per unit value. Since air is a mixture of gases, it can be compressed. If the air in one container is under half as much pressure as an equal amount of air in an identical container, the air under the greater pressure weighs twice as much as that in the container under lower pressure. The air under greater pressure is twice as dense as that in the other container. For the equal weight of air, that which is under the greater pressure occupies only half the volume of that under half the pressure. The density of gases is governed by the following rules. 1. Density varies in direct proportion with the pressure. 2. Density varies inversely with temperature. Thus, air at high altitudes is less dense than air at low altitudes, and a mass of hot air is less dense than a mass of cool air. Changes in density affect the aerodynamic performance of aircraft with the same horsepower. An aircraft can fly faster at high altitude where the density is low than at low altitude where the density is greater. This is because air offers less resistance to the aircraft when it contains a smaller number of particles per unit of volume. Humidity. Humidity is the amount of water vapor in the air. The maximum amount of water vapor that air can hold varies with the temperature. The higher the temperature of the air, the more water vapor it can absorb. Absolute humidity is the weight of water vapor in a unit volume of air. Relative humidity is the ratio in percent of the moisture actually in the air to the moisture it would hold if it were saturated at the same temperature and pressure. Assuming that the temperature and pressure remain the same, the density of air varies inversely with the humidity. On damp days, the air density is less than on dry days. For this reason, an aircraft requires a longer runway for takeoff on damp days than it does on dry days. By itself, water vapor weighs approximately 5/8 as much as an equal amount of perfectly dry air. Therefore, when air contains water vapor, it is not as heavy as dry air containing no moisture. Aerodynamics and the laws of physics. The law of conservation of energy states that energy may neither be created nor destroyed. Motion is the act or process of changing the place or position. An object may be in motion with respect to one object and motionless with respect to another. For example, a person sitting quietly in an aircraft flying at 200 knots is at rest, or motionless with respect to the aircraft. However, the person in the aircraft in motion with respect to the air and to the earth air has no force or power except pressure, unless it is in motion. Whenever it is moving, however, its force becomes apparent. A moving object in motionless air has a force exerted on it as a result of its own motion. It makes no difference in the effect then, whether an object is moving with respect to the air or the air is moving with respect to the object. The flow of air around an object caused by the movement of either the air or the object or both is called the relative wind. Velocity and acceleration. The terms speed and velocity are often used interchangeably, but they do not have the same meaning. Speed is the rate of motion in relation to time, and velocity is the rate of motion in a particular direction in relation to time. An aircraft starts from New York City and flies 10 hours at an average speed of 260 miles per hour. At the end of this time, the aircraft may be over the Atlantic Ocean, Pacific Ocean, Gulf of Mexico, or if its flight were in a circular path, it may even be back over New York City. If the same aircraft flew at a velocity of 260 miles in a southwestward direction, it would arrive in Los Angeles in about 10 hours. Only the rate of motion is indicated in the first example and denotes the speed of the aircraft. In the last example, the particular direction is included with the rate of motion, thus denoting the velocity of the aircraft. Acceleration is defined as the rate of change of velocity. An aircraft increasing in velocity is an example of positive acceleration, while another aircraft reducing its velocity is an example of negative acceleration or deceleration. Newton's law of motion. The fundamental laws governing the action of air about a wing are known as Newton's laws of motion. Newton's first law is normally referred to as the law of inertia. It simply means that a body at rest does not move unless force is applied to it. If a body is moving at uniform speed in a straight line, force must be applied to increase or decrease the speed. According to Newton's law, since air has mass, it is a body. When an aircraft is on the ground with its engine off, inertia keeps the aircraft at rest. An aircraft is moved from its state of rest by the thrust force created by a propeller, or by the expanding exhaust, or both. When an aircraft is flying at uniform speed in a straight line, inertia tends to keep the aircraft moving. Some external force is required to change the aircraft from its flight path. Newton's second law states that if a body moving with uniform speed is acted upon by an external force, the change of motion is proportional to the amount of force and motion takes place in the direction in which the force acts. This law may be stated mathematically as follows. Force equals mass times acceleration. F equals ma. If an aircraft is flying against a headwind, it is slowed down. If the wind is coming from either side of the aircraft's heading, the aircraft is pushed off course unless the pilot takes corrective action against the wind direction. Newton's third law is the law of action and reaction. This law states that for every action, force, there is an equal and opposite reaction, force. This law can be illustrated by the example of firing a gun. The action is the forward movement of the bullet, while the reaction is the backward recoil of the gun. The three laws of motion that have been discussed apply to the theory of flight. In many cases, all three laws may be operating on an aircraft at the same time. Bernoulli's principle in subsonic flow. Bernoulli's principle states that when a fluid, air, flowing through a tube reaches a constriction or narrowing of the tube, the speed of the fluid flowing through that constriction is increased and its pressure is decreased. The cambered or curved surface of an airfoil, the wing, affects the airflow exactly as a constriction in a tube affects airflow. Diagram A of Figure 2-2 illustrates the effect of air passing through a constriction in a tube. In Diagram B, air is flowing past a cambered surface, such as an airfoil, and the effect is similar to that of air passing through a restriction. As the air flows over the upper surface of an airfoil, its velocity increases and its pressure decreases. An area of low pressure is formed. There is an area of greater pressure on the lower surface of the airfoil, and this greater pressure tends to move the wing upward. The difference in pressure between the upper and lower surfaces of the wing is called lift. 3/4 of the total lift of an airfoil is the result of the decrease in pressure over the upper surface. The impact of air on the undersurface of an airfoil produces the other 1/4 of the total lift. An airfoil is a surface designed to obtain lift from the air through which it moves. Thus, it can be stated that any part of the aircraft that converts air resistance into lift is an airfoil. The profile of a conventional wing is an excellent example of an airfoil. Notice that the top surface of the wing profile has a greater curvature than the lower surface. The difference in curvature of the upper and lower surfaces of the wing builds the lift force. Air flowing over the top surface of the wing must reach the trailing edge of the wing in the same amount of time as the air flowing under the wing. To do this, the air passes over the top surface, moves at a greater velocity than the air passing below the wing. Because of the greater distance, it must travel along the top surface. This increased velocity, according to Bernoulli's principle, means a corresponding decrease in pressure on the surface. Thus, a pressure differential is created between the upper and lower surfaces of the wing, forcing the wing upward in the direction of lower pressure. Within limits, lift can be increased by increasing the angle of attack, wing area, velocity, density of air, or by changing the shape of the airfoil. When the force of lift on an aircraft's wing equals the force of gravity, the aircraft maintains level flight. Shape of the airfoil. Individual airfoil section properties differ from those properties of the wing or aircraft as a whole because of the effect of the wing platform. A wing may have various airfoil sections from root to tip with taper, twist, and swept back. The resulting aerodynamic properties of the wing are determined by the action of each section along the span. The shape of the airfoil determines the amount of turbulence or friction that it produces, consequently affecting the efficiency of the wing. Turbulence and skin friction are controlled mainly by the fineness ratio, which is defined as the ratio of the chord of the airfoil to the maximum thickness. If the wing has a high fineness ratio, it is a very thin wing. A thick wing has a low fineness ratio. A wing with a high fineness ratio produces a large amount of skin friction. A wing with a low fineness ratio produces a large amount of turbulence. The best wing is a compromise between these two extremes to hold both turbulence and friction to a minimum. The efficiency of a wing is measured in terms of lift to drag ratio. This ratio varies with the angle of attack but reaches a definite maximum value for a particular angle of attack. At this angle, the wing has reached its maximum efficiency. The shape of the airfoil is the factor that determines the angle of attack at which the wing is most efficient. It also determines the degree of efficiency. Research has shown that the most efficient airfoils for general use have the maximum thickness occurring about 1/3 of the way back from the leading edge of the wing. High lift wings and high lift devices for wings have been developed by shaping the airfoils to produce the desired effect. The amount of lift produced by an airfoil increases with an increase in wing camber. Camber refers to the curvature of an airfoil above and below the chord line surface. Upper camber refers to the upper surface. Lower camber to the lower surface. And mean camber to the mean line of the section. Camber is positive when departure from the chord line is outward and negative when it is inward. Thus, high lift wings have a large positive camber on the upper surface and a slightly negative camber on the lower surface. Wing flaps cause an ordinary wing to approximate the same condition by increasing the upper camber and by creating a negative lower camber. It is also known that the larger the wingspan as compared to the chord, the greater the lift obtained. This comparison is called aspect ratio. The higher the aspect ratio, the greater the lift. In spite of the benefits from an increase in aspect ratio, it was found that definite limitations were defined by structural and drag considerations. On the other hand, an airfoil that is perfectly streamlined and offers little wind resistance sometimes does not have enough lifting power to take the aircraft off the ground. Thus, modern aircraft have airfoils which strike a medium between extremes. The shape depending on the purposes of the aircraft for which it is designed. Angle of incidence. The acute angle the wing chord makes with the longitudinal axis of the aircraft is called the angle of incidence, or the angle of wing setting. Figure 2.4. The angle of incidence in most cases is fixed built-in angle. When the leading edge of the wing is higher than the trailing edge, the angle of incidence is said to be positive. The angle of incidence is negative when the leading edge is lower than the trailing edge of the wing. Angle of attack. Before beginning the discussion on angle of attack and its effect on airfoils, first consider the terms chord and center of pressure, as illustrated in Figure 2.5. The chord of an airfoil or wing section is an imaginary straight line that passes through the section from the leading edge to the trailing edge, as shown in Figure 2.5. The chord line provides one side of an angle that ultimately forms the angle of attack. The other side of the angle is formed by a line indicating the direction of the relative airstream. Thus, angle of attack is defined as the angle between the chord line of the wing and the direction of the relative wind. This is not to be confused with the angle of incidence, illustrated in Figure 2.4, which is the angle between the chord line of the wing and the longitudinal axis of the aircraft. On each part of an airfoil or wing surface, a small force is present. This force is of a different magnitude and direction from any forces acting on other areas forward or rearward from this point. It is possible to add all of these small forces mathematically. That sum is called the resultant force, lift. This resultant force has magnitude, direction, and location, and can be represented as a vector, as shown in Figure 2.5. The point of intersection of the resultant force line with the chord line of the airfoil is called the center of pressure. The center of pressure moves along the airfoil chord as the angle of attack changes. Throughout most of the flight direction, the center of pressure moves forward with increasing angle of attack and rearward as the angle of attack decreases. The effect of increasing angle of attack on the center of pressure is shown in Figure 2.6. The angle of attack changes as the aircraft's attitude changes. Since the angle of attack has a great deal to do with determining lift, it is given primary consideration when designing airfoils. In a properly designed airfoil, the lift increases as the angle of attack is increased. When the angle of attack is increased gradually toward a positive angle of attack, the lift component increases rapidly up to a certain point and then suddenly begins to drop off. During this action, the drag component increases slowly at first, then rapidly as lift begins to drop off. When the angle of attack increases to the angle of maximum lift, the burble point is reached. This is known as the critical angle. When the critical angle is reached, the air ceases to flow smoothly over the top surface of the airfoil and begins to burble or eddy. This means that air breaks away from the upper camber line of the wing. What was formerly the area of decreased pressure is now filled by this burbling air. When this occurs, the amount of lift drops and drag becomes excessive. The force of gravity exerts itself, and the nose of the aircraft drops. This is a stall. Thus, the burble point is the stalling angle. As previously seen, the distribution of the pressure forces over the airfoil varies with the angle of attack. The application of the resultant force, or center of pressure, varies correspondingly. As this angle increases, the center of pressure moves forward. As the angle decreases, the center of pressure moves back. The unstable travel of the center of pressure is characteristic of almost all airfoils. Boundary layer. In the study of physics and fluid mechanics, a boundary layer is that layer of fluid in the immediate vicinity of a bounding surface. In relation to an aircraft, the boundary layer is the part of the airflow closest to the surface of the aircraft. In designing high-performance aircraft, considerable attention is paid to controlling the behavior of the boundary layer to minimize pressure drag and skin friction drag. Thrust and drag. An aircraft in flight is the center of a continuous battle of forces. Actually, this conflict is not as violent as it sounds, but it is a key to all maneuvers performed in the air. There is nothing mysterious about these forces. They are definite and known. The directions in which they act can be calculated, and the aircraft itself is designed to take advantage of each of them. In all types of flying, flight calculations are based on magnitude and direction of four forces: weight, lift, drag, and thrust. An aircraft in flight is acted upon by four forces: gravity or weight, the force that pulls the aircraft toward the earth. Weight is the force of gravity acting downward upon everything that goes into the aircraft, such as the aircraft itself, crew, fuel, and cargo. Lift, the force that pushes the aircraft upward. Lift acts vertically and counteracts the effects of weight. Thrust, the force that moves the aircraft forward. Thrust is the forward force produced by the power plant that overcomes the force of drag. Drag, the force that exerts a braking action to hold the aircraft back. Drag is a backward deterrent force and is caused by the disruption of the airflow by the wings, fuselage, and protruding objects. These four forces are in perfect balance only when the aircraft is in straight and level, unaccelerated flight. The forces of lift and drag are the direct result of the relationship between the relative wind and the aircraft. The force of lift always acts perpendicular to the relative wind, and the force of drag always acts parallel to and in the same direction as the relative wind. These forces are actually the components that produce a resultant lift force on the wing. Weight has a definite relationship with lift and thrust with drag. These relationships are quite simple, but very important in understanding the aerodynamics of flying. As stated previously, lift is the upward force on the wing perpendicular to the relative wind. Lift is required to counteract the aircraft's weight, caused by the force of gravity acting on the mass of the aircraft. This weight force acts downward through a point called the center of gravity. The CG is the point at which all the weight of the aircraft is considered to be concentrated. When the lift force is in equilibrium with the weight force, the aircraft neither gains nor loses altitude. If lift becomes less than weight, the aircraft loses altitude. When the aircraft is greater than the weight, the aircraft gains altitude. When the lift is greater than the weight, the aircraft gains altitude. Wing area is measured in square feet and includes the part blanked out by the fuselage. Wing area is adequately described as the area of the shadow cast by the wing at high noon. Tests show that lift and drag forces acting on a wing are roughly proportional to the wing area. This means that if the wing is doubled, all other variables remaining the same, the lift and drag created by the wing is doubled. If the area is tripled, lift and drag are tripled. Drag must be overcome for the aircraft to move, and movement is essential to obtain lift. To overcome drag and move the aircraft forward, another force is essential. This force is thrust. Thrust is derived from jet propulsion are from a propeller and engine combination. Jet propulsion theory is based on Newton's third law of motion. The turbine engine causes a mass of air to be moved backward at high velocity, causing a reaction that moves the aircraft forward. In a propeller-engine combination, the propeller is actually two or more revolving airfoils mounted on a horizontal shaft. The motion of the blades through the air produces lift similar to the lift of the wing, but acts on a horizontal direction, pulling the aircraft forward. Before the aircraft begins to move, thrust must be exerted. The aircraft continues to move and gain speed until thrust and drag are equal. In order to maintain a steady speed, thrust and drag must remain equal, just as lift and weight must be equal for steady horizontal flight. Increasing the lift means that the aircraft moves upward, whereas decreasing the lift so that it is less than the weight causes the aircraft to lose altitude. A similar rule applies to the two forces of thrust and drag. If the revolutions per minute (RPM) of the engine is reduced, the thrust is lessened and the aircraft slows down. As long as the thrust is less than the drag, the aircraft travels more and more slowly until its speed is insufficient to support it in the air. Likewise, if the RPM of the engine is increased, thrust becomes greater than drag, and the speed of the aircraft increases. As long as the thrust continues to be greater than the drag, the aircraft continues to accelerate. When drag equals thrust, the aircraft flies at a steady speed. The relative motion of the air over an object that produces lift also produces drag. Drag is the resistance of the air to objects moving through it. If an aircraft is flying on a level course, the lift force acts vertically to support it while the drag force acts horizontally to hold it back. The total amount of drag on an aircraft is made up of many drag forces, but this handbook considers three: parasite drag, profile drag, and induced drag. Parasite drag is made up of any combination of different drag forces. Any exposed object on an aircraft offers some resistance to the air, and the more objects in the airstream, the more parasite drag. While parasite drag can be reduced by reducing the number of exposed parts to as few as practical and streamlining their shape, skin friction is a type of parasite drag most difficult to reduce. No surface is perfectly smooth. Even machine surfaces have a ragged, uneven appearance when inspected under magnification. These ragged surfaces deflect the air near the surface, causing resistance to smooth airflow. Skin friction can be reduced by using glossy, smooth finishes and eliminating protruding rivet heads, roughness, or other irregularities. Profile drag may be considered the parasite drag of the airfoil. The various components of parasite drag are all of the same nature as profile drag. The action of the airfoil that creates lift also causes induced drag. Remember, the pressure above the wing is less than atmospheric pressure. The pressure below the wing is equal to or greater than the atmospheric pressure. Since fluids always move from high pressure toward low pressure, there is a spanwise movement of air from the bottom of the wing outward from the fuselage and upward around the wingtip. This flow of air results in spillage over the wingtip, thereby setting up a whirlpool of air called a vortex. The air on the upper surface has a tendency to move in toward the fuselage and off the trailing edge. This air current forms a similar vortex at the inner portion of the trailing edge of the wing. These vortices increase drag because the turbulence produced and constitute induced drag. Just as lift increases with an increase in angle of attack, induced drag also increases as the angle of attack becomes greater. This occurs because, as the angle of attack is increased, the pressure difference between the top and bottom of the wing becomes greater. This causes more violent vortices to be set up, resulting in more turbulence and more induced drag. Center of gravity. Gravity is the pulling force that tends to draw all bodies within the Earth's gravitational field to the center of the Earth. The CG may be considered the point at which all weight of the aircraft is concentrated. If the aircraft was supported at its exact CG, it would balance in any position. CG is of major importance in an aircraft, for its position has a great bearing upon stability. The CG is determined by the general design of the aircraft. The designers estimate how far the center of pressure travels. They then fix the center of gravity in front of the center of pressure for the corresponding flight speed in order to provide an adequate restoring moment for flight equilibrium. The axis of an aircraft. Whenever an aircraft changes its flight attitude, it must turn about one or more of three axes. Figure 210 shows the three axes, which are imaginary lines passing through the center of the aircraft. The axes of an aircraft can be considered as imaginary axles around which the aircraft turns like a wheel. At the center, where all three axes intersect, each is perpendicular to the other two. The axis that extends lengthwise through the fuselage from the nose to the tail is called the longitudinal axis. The axis that extends crosswise from wingtip to wingtip is the lateral or pitch axis. The axis that passes through the center from top to bottom is called the vertical or yaw axis. Roll, pitch, and yaw are controlled by three control surfaces. Roll is produced by the ailerons, which are located at the trailing edges of the wings. Pitch is affected by the elevators, the rear portion of the horizontal tail assembly. Yaw is controlled by the rudder, the rear portion of the vertical tail assembly. Stability and control. An aircraft must have sufficient stability to maintain a uniform flight path and recover from the various upsetting forces. Also, to achieve the best performance, the aircraft must have the proper response to the movement of the controls. Control is the pilot action of moving the flight controls, providing the aerodynamic force that induces the aircraft to follow a desired flight path. When an aircraft is said to be controllable, it means that the aircraft responds easily and promptly to movement of the controls. Different control surfaces are used to control the aircraft about each of the three axes. Moving the control surfaces on an aircraft changes the airflow over the aircraft surface. This, in turn, creates changes in the balance of forces acting to keep the aircraft flying straight and level. Three terms that appear in any discussion of stability and control are stability, maneuverability, and controllability. Stability is the characteristic of an aircraft that tends to cause it to fly, hands off, in a straight and level flight path. Maneuverability is the characteristic of an aircraft to be directed along a desired flight path and to withstand the stresses imposed. Controllability is a quality of the response of an aircraft to the pilot's commands while maneuvering the aircraft. Static stability. An aircraft is in a state of equilibrium when the sum of all the forces acting on the aircraft in all the moments is equal to zero. An aircraft in equilibrium experiences no accelerations and the aircraft continues in a steady condition of flight. A gust of wind or a deflection of the controls disturbs the equilibrium, and the aircraft experiences acceleration due to the imbalance of moment or force. Three types of static stability are defined by the character of movement following some disturbance of equilibrium. Positive static stability exists when the disturbed object tends to return to equilibrium. Negative static stability or static instability exists when the disturbed object tends to continue in the direction of disturbance. Neutral static stability exists when the disturbed object has neither tendency, but remains in equilibrium in the direction of disturbance. These three types of stability are illustrated in Figure 2.11. Dynamic stability. While static stability deals with the tendency of a displaced body to return to equilibrium, dynamic stability deals with the resulting motion with time. If an object is disturbed from equilibrium, the time history of the resulting motion defines the dynamic stability of the object. In general, an object demonstrates positive dynamic stability if the amplitude of motion decreases with time. If the amplitude of motion increases with time, the object is said to possess dynamic instability. Any aircraft must demonstrate the required degrees of static and dynamic stability. If an aircraft were designed with static instability and a rapid rate of dynamic instability, the aircraft would be very difficult, if not impossible, to fly. Usually, positive dynamic stability is required in an aircraft design to prevent objectionable continued oscillations of the aircraft. Longitudinal stability. When an aircraft has a tendency to keep a constant angle of attack with reference to the relative wind, i.e., it does not tend to put its nose down or dive or lift its nose and stall, it is said to have longitudinal stability. Longitudinal stability refers to motion and pitch. The horizontal stabilizer is the primary surface which controls longitudinal stability. The action of the stabilizer depends upon the speed and angle of attack of the aircraft. Directional stability. Stability about the vertical axis is referred to as directional stability. The aircraft should be designed so that when it is in straight and level flight, it remains on its course heading, even though the pilot takes their hands and feet off the controls. If an aircraft recovers automatically from a skid, it has been well designed for directional balance. The vertical stabilizer is the primary surface that controls directional stability. Directional stability can be designed into an aircraft where appropriate by using a large dorsal fin, a long fuselage, and swept-back wings. Lateral stability. Motion about the aircraft's longitudinal fore and aft axis is a lateral or rolling motion. The tendency to return to the original attitude from such motion is called lateral stability. Dutch roll. A Dutch roll is an aircraft motion consisting of an out-of-phase combination of yaw and roll. Dutch roll stability can be artificially increased by the installation of a yaw damper. Primary flight controls. The primary controls are the aileron, elevators, and the rudder, which provide the aerodynamic force to make the aircraft follow a desired path. Figure 210. The flight control surfaces are hinged or movable airfoils designed to change the attitude of the aircraft by changing the airflow over the aircraft surface during flight. These surfaces are used for moving the aircraft about its three axes. Typically, the ailerons and elevators are operated from the flight deck by means of a control stick, a wheel, and a yoke assembly, and on some of the newer design aircraft, a joystick. The rudder is normally operated by foot pedals on most aircraft. Lateral control is the banking movement or roll of an aircraft that is controlled by the ailerons. Longitudinal control is the climb and dive movement or pitch of an aircraft that is controlled by the elevator. Directional control is the left and right movement or yaw of an aircraft that is controlled by the rudder. Trim controls. Included in the trim controls are the trim tabs, servo tabs, balance tabs, and spring tabs. Trim tabs are small airfoils recessed into the trailing edges of the primary control surfaces. Figure 212. Trim tabs can be used to correct any tendency of the aircraft to move toward an undesirable flight attitude. Their purpose is to enable the pilot to trim out any unbalanced condition which may exist during flight, without exerting any pressure on the primary controls. Servo tabs, sometimes referred to as flight tabs, are used primarily on the large main control surfaces. They aid in moving the main control surface and holding it in the desired position. Only the servo tab moves in response to movement by the pilot of the primary flight controls. Balance tabs are designed to move in the opposite direction of the primary flight control. Thus, aerodynamic forces acting on the tab assist in moving the primary control surface. Spring tabs are similar in appearance to trim tabs, but serve an entirely different purpose. Spring tabs are used for the same purpose as hydraulic actuators, to aid the pilot in moving the primary control surface. Figure 213 indicates how each trim tab is hinged to its parent primary control surface, but is operated by an independent control. Auxiliary lift devices. Included in the auxiliary lift devices group of flight control surfaces are the wing flaps, spoilers, speed brakes, slats, leading edge flaps, and slots. The auxiliary groups may be divided into two subgroups. those whose primary purpose is lift augmenting, and those whose primary purpose is lift decreasing. In the first group are the flaps, both trailing edge and leading edge, slats, and slots. The lift decreasing devices are speed brakes and spoilers. Lift augmenting. Flaps are located on the trailing edge of the wing and are movable to increase the wing area, thereby increasing lift on takeoff and decreasing the speed during landing. These airfoils are retractable and fare into the wing contour. Others are simply a portion of the lower skin which extends into the airstream, thereby slowing the aircraft. Leading edge flaps are also referred to as slats. Are airfoils extended from and retracted into the leading edge of the wing. Some installations create a slot, an opening between the extended airfoil and the leading edge. Figure 214. At low airspeeds, this slot increases lift and improves handling characteristics, allowing the aircraft to be controlled at airspeeds below the normal landing speed. Other installations have permanent slots built into the leading edge of the wing. At cruising speeds, the trailing edge and leading edge flaps, or slats, are retracted into the wing proper. Slats are movable control surfaces attached to the leading edges of the wings. When the slat is closed, it forms the leading edge of the wing. When in the open position, extended forward, a slot is created between the slat and the wing leading edge. At low airspeeds, this increases lift and improves handling characteristics, allowing the aircraft to be controlled at airspeeds below the normal landing speed. Lift decreasing. Lift decreasing devices are the speed brakes, spoilers. In some installation, there are two types of spoilers. The ground spoiler is extended only after the aircraft is on the ground, thereby assisting in the braking action. The flight spoiler assists in lateral control by being extended whenever the aileron on the wing is rotated up. When actuated as speed brakes, the spoiler panels on both wings raise up. In-flight spoilers may also be located along the sides, underneath the fuselage, or back at the tail. Figure 216. In some aircraft designs, the wing panel on the up aileron side rises more than the wing panel on the down aileron side. This provides speed brake operation and lateral controls simultaneously. Winglets. Winglets are near vertical extensions of the wingtip that reduces the aerodynamic drag associated with vortices that develops at the wingtips as the airplane moves through the air. By reducing the induced drag at the tips of the wings, fuel consumption goes down and range is extended. Figure 217 shows an example of a Learjet 60 with winglets. Canard wings. A canard wing aircraft is an airframe configuration of a fixed-wing aircraft in which a small wing or horizontal airfoil is ahead of the main lifting surfaces. rather than behind them as in a conventional aircraft. The canard may be fixed, movable, or designed with elevators. Good examples of aircraft with canard wings are the Rutan Vereis and Beechcraft 2000 Starship in Figure 218 and Figure 219. Wing fences. Wing fences are flat metal vertical plates fixed to the upper surface of the wing. They obstruct spanwise airflow along the wing and prevent the entire wing from stalling at once. They are often attached on swept-wing aircraft to prevent the spanwise movement of air at high angle of attack. Their purpose is to provide better slow speed handling and stall characteristics. Control systems for large aircraft. Mechanical control. This is the basic type of system that was used to control early aircraft and is currently used in smaller aircraft where aerodynamic forces are not excessive. The controls are mechanical and manually operated. The mechanical system of controlling an aircraft can include cables, push-pull tubes, and torque tubes. The cable system is the most widely used because deflections of the structure to which it is attached do not affect its operation. Some aircraft incorporate control systems that are a combination of all three. These systems incorporate cable assemblies, cable guides, linkage, adjustable stops, and control surface snubber or mechanical locking devices. These surface locking devices, usually referred to as a gust lock, limits the external wind forces from damaging the aircraft while it is parked or tied down. Hydromechanical control. As the size, complexity, and speed of the aircraft increase, actuation of controls in flight become more difficult. It soon became apparent that the pilot needed assistance to overcome the aerodynamic forces to control aircraft movement. Spring tabs, which were operated by the conventional control system, were moved so that the airflow over them actually moved the primary control surface. This was sufficient for aircraft operating in the lowest of the high-speed ranges, 250 to 300 miles per hour. For higher speeds, a power-assisted hydraulic control system was designed. Conventional cable or push-pull tube system linked the flight deck controls with the hydraulic system. With the system activated, the pilot's movement of a control causes the mechanical link to open servo valves, thereby directing hydraulic fluid to actuators, which convert hydraulic pressure into control surface movements. Because of the efficiency of the hydromechanical flight control system, the aerodynamic forces on the control surfaces cannot be felt by the pilot, and there is a risk of overstressing the structure of the aircraft. To overcome this problem, aircraft designers incorporated artificial feel systems into the design that provided increased resistance to the controls at higher speeds. Additionally, some aircraft with hydraulically powered control systems are fitted with a device called a stick shaker, which provides an artificial star warning to the pilot. Fly-by-wire control. The fly-by-wire control system employs electrical signals that transmit the pilot's actions from the flight deck through a computer to the various flight control actuators. The fly-by-wire system evolved as a way to reduce the system weight of the hydromechanical system. reduce maintenance costs, and improve reliability. Electronic fly-by-wire control systems can respond to changing aerodynamic conditions by adjusting flight control movements so that the aircraft response is consistent for all flight conditions. Additionally, the computers can be programmed to prevent undesirable and dangerous characteristics, such as stalling and spinning. Many of the new military high-performance aircraft are not aerodynamically stable. This characteristic is designed into the aircraft for increased maneuverability and responsive performance. Without the computers reacting to the instability, the pilot would lose control of the aircraft. The Airbus A320 was the first commercial airliner to use fly-by-wire controls. Boeing used